These slides have a slightly different look from the others because I am also recording this specifically for groups of people that I'm working with, my students and a bunch of postdocs and a variety of people. So I've used Sweave instead of Quarto to make these slides. It's actually probably a good thing to have a variety of slide sources. And I'll just point out that this nice looking beast was made by Gemini. I asked for a virus that would look bizarre. Anyway, so here what I want to do is spend some time explaining how to use R to play with continuous time Markov chains. And I'm going to make it clear from the beginning that this is not a course on continuous time Markov chains. This is a course on the use of R to do this. So if you want more details about continuous time Markov chains, there are a variety of resources to look at. Here we're really focusing on how to use R to look at Markov chains. So what I'm going to do is spend a very little time explaining continuous time Markov chains, and this is really, as I said, just in passing. And then I'm going to explain a variety of aspects of dealing with Markov chains in the R programming language. So the first thing is, what's the Markov chain? Continuous time Markov chain, they're very similar to discrete time Markov chains, which are more known, except in the way that they handle the time between events. So a discrete time Markov chain is very much like a sequence where the time between events in a sequence is a prescribed quantity. In a continuous time Markov chain, the transition occurs with some random quantity. Okay? And there is a inter-event time. So the time between two transitions is an exponentially distributed random variable that depends on the weight of the probabilities of the events in a chain. And I'll point out that continuous time Markov chains, one of the reasons they're really useful, in my view, for a modeler to use, is that they are very, very similar to ordinary differential equations. As a matter of fact, if you are using a continuous time Markov chain and a linear differential equation, then you have that the mean of your continuous time Markov chain absolutely matches the differential equation. The same is not true with nonlinear equations, but they are still very, very similar, and a lot of the properties are shared between the two types of problems. But as I said, this is not the point of this presentation, which has to do only with the numerical, essentially, treatment of this. So first thing is to understand how to go from an ODE to a continuous time Markov chain. And once you understand this, then it becomes very, very simple to implement Markov chains in a continuous manner in your models. So I will just point out that converting a Markov, an ODE, and I stress a compartmental ODE. Okay, this is not true for all ODEs, but at least when you're using a compartmental ODE, so the ones that arise, for example, in many ecological or epidemiological applications, when you have something that's compartmental, it is very, very easy to do the conversion, to obtain a continuous time Markov chain from the ODE. So the main idea is that a continuous time, an ODE to start with, focuses on the flows in and out of compartments, whereas a continuous time Markov chain focuses on the transitions between compartments. Okay, so let me illustrate this. So on the left here, I have, so if I think about an SIS epidemic model, so essentially the simplest epidemic model that I could think of, where individuals are susceptible and infectious. Once they become infected by the disease, they become immediately infectious with the disease, and once they recover, they immediately become susceptible again with the disease. Okay, so this is, and there is no demography. I'm assuming that the total population is fixed, and so individuals just go back and forth between the two compartments, S and I. So if I'm looking at the ODE, what I'm doing is when you're writing the ordinary differential equation, you're focusing on the inflows and outflows from a compartment. So for instance, if I look at that S compartment here, and I'm wondering how to describe its, how to write down an equation for the evolution of the numbers in S, I would say, well, there are individuals leaving S at the rate minus beta Si, and there are individuals entering S at the rate gamma I. If gamma is the recovery rate and beta is the infection coefficient. Okay, so that means that S prime, the evolution of the number of individuals in S, will be minus beta Si plus gamma I. And likewise, I move to the other end of the model, and I'm looking at the I equation. And for that one, I'm the same way. I'm doing mass balance, essentially. What is entering, what is leaving. And what is entering is beta Si, and what is leaving is gamma I. So in this case, the equation for I prime is beta Si minus gamma I. Okay. Now, if I want to switch to a continuous time Markov chain, I take the same model, but I switch my focus from focusing on the states, as I did with the ODE, I now focus on the transitions themselves. Okay, so the transitions are beta Si means that an individual moved from the S compartment to the I compartment. And gamma I means that an individual moved here from I into S. Okay, so that is the only difference between the two models. And so essentially, when I want to write the continuous time Markov chain, I'm going to do so by just saying, well, that transition that transforms S into one less S individual and one more I individual, that's a new infection. Its weight, I'm going to use exactly the same weight as is used for the rate of movement from S to I. Okay, so the weight of that transition is beta Si. And the transition that goes from, oops, this should be, no, that's good, sorry. The transition that sees an increase of the number of susceptibles and a decrease of the number of infectious, that's a recovery, and that transition has weight gamma I. And the sum of those weights, if I divide those weights by the sum of the weights, I get a number that sums to 1. So that's essentially the probabilities that those transitions occur. Okay. If I want to consider a more complex process where I have, for instance, demography, when things don't change that much, if you see, I'm going to, of course, have transitions which, in this case, don't change both variables, they just change one of them, okay? One of them is, okay, if I have birth of a susceptible individual, that means my susceptible population is increasing by 1. Or if I have death of a susceptible individual, that population is decreasing by 1. The new infection we've already seen, but we can also lose infectious, and you can see that I'm losing an infectious here by death. And so those rates are those that I've added. This is a typical way of writing an SIS model if you have constant birth but death at a per capita rate D and well, D in both compartments. So I've added these two weights. So that means that when I'm computing my transition probabilities, I need to divide by the new sum of weights, which now includes B, DS, DI, and the rates we already had. Okay? So those rates of transitions are the rates that you're using in your ODE, but they are used to compute the probability of transition. And one thing that I will add before I move any further and I show you a last example is that what you can see is the movements here, I mean the transitions involve integer numbers of individuals, which is different from an ODE, okay? Because in the ODE you have a rate of change of a population in S, for example, and that rate of change means that the population in S is a continuous real valued, non-negative real valued variable, whereas here we have integer valued variables, which in many cases, if you're counting individuals and the like, is actually a very good thing to have. Individuals are not fractions of individuals, they are actual numbers. Okay. One last example, this is the Kermack and McKendrick model. There's no demography here again, but here I have the flow from S to I, which has the rate beta SI, the flow from I into R, the removed compartment, which is gamma I, and therefore this is the model. And you can see that actually the transition probabilities are the same as in the SIS model, but in this case, we don't go back to S, we move from I into R, but the model is essentially the same. Okay, so now how do you simulate those objects? So the main workhorse for doing this is called the Gillespie algorithm. So this was derived in '76 by Daniel Gillespie, who's a computational chemist. Okay, so the type of model that they were using were massive simulation models for computational chemistry. It's also known as the stochastic simulation algorithm. There are other names in other contexts. I don't remember, there's another name in physics, for example. The algorithm bears a number of names, but essentially I'll just call it Gillespie because that's who came up with that specific implementation. It's an extremely simple algorithm, and I'm going to show you how to use it or to write that algorithm, even though in later in these slides I will be arguing that you should probably be using a package that does it. But it's a good starting point, and to understand what's happening, I think it is a very interesting problem to look at. So the Gillespie algorithm works this way. So suppose you start, suppose you have x of t is the state of your system at time t. And that could be a vector, etc. I'm not making it clear for the moment. So if x of t is your state at time t and your initial condition at time t0 is x0, then we define what are called propensity functions, AI, of what are called the elementary reactions. And so to come back to what I was just showing you, the propensity functions are essentially those rates that we were talking about. Okay, the elementary reactions are what I've called effect here, so new infection, etc. And this is what they result in, and these are the propensity functions. Okay. So you start by setting your time to whatever you want it to be, and your state to your initial state. And while your time is less than some final time that you've decided on, what you're going to do is you're going to sum the propensity functions applied to the state. Okay, so I will show you an example in a minute. Okay, so but just to explain, so this is so the propensity functions are those rates that I had before, but those rates of course depend on the state of the system. So beta Si depends on S of t and I of t. It's not always the same value, and likewise gamma I depends on I of t. So this is what this means. So sigma of t is just the sum of the weights, and then what you do is this sum of weights actually determines the time at which the next event is going to take place. That time is an exponentially, I use this symbol for exponentially, that time is an exponentially distributed random variable. Okay, oh, I mean, it's drawn from an exponentially distributed random variable. So you compute the weight of the events at the given state of the system at the instant where you are, and that determines when the next event is going to take place. You also take a uniformly distributed random variable in the interval 0, 1, and then what you're looking for is the smallest integer so that the sum of the weighted values, the partial sum of the weighted values is larger. So if you want, you could also divide by zeta. Oh, that should be, the zeta is here. So you could divide by the total weights here. But so what you want is the first value, which is larger than that random number times this. Okay, so this here is xi. So xi is what I've denoted beta Si plus gamma I here, for example. And so what you want to know is whether you are with a value that is between 0 and beta Si over xi, or between beta Si and 1 in this case, because the sum of the two is 1. Okay, so this is, and that value determines which of the potential events is taking place. Okay. Then you effect that change, and you move the time forward by that amount of that random value that you found at the beginning. Okay, so, and you repeat until the time is big enough. Let me, just a very quick remark, this is essentially not relevant in R, but I'll just make it. Sometimes you will use some code that doesn't have an exponential number generator, so this is more for people who would want to implement this in old style C, for example. In that case, you can only draw at random uniformly, and in that, what this is showing you is how to transform a uniformly distributed number into a exponentially distributed number. Okay, so let's forget about this for a moment, but just to explain where this is coming from. So let me show you the SIS model. I'm going to simplify things because, as I pointed out, the SIS model that I was showing you earlier has only the has a constant total population, so I can just say that S is the total population minus I. Okay, so I can just focus on the I equation. So same as we said before, we set the initial time to t0, we set the initial state to I of t0, and then we repeat while our time has not reached the final value. The sum of the events, the weights of the events, okay, the sum of the propensity functions evaluated at the state is beta p star, which is, I take my total population, minus, I've used a little I, this is a classic thing in Markov chains, but don't worry about it, this is I of t, okay? So this is S of t, essentially, times I of t plus gamma I of t. From that psi, we derive a value tau t for the time at which the next event is going to take place. One way we can do that thing about finding which interval is to make a vector that has, well, here I've only got two events possible, infection or recovery. So in the first element of the vector, I would just say, okay, this is the weight of the infection event. And psi t here is, of course, the sum of the weights. I divide it by psi t to get the probability. Okay, the numbers in V are then between 0 and 1, this being the probability that the first event occurs, and this being the probability that the first event or the second event occurs, because there's only two events, as I was saying. Draw zeta from a uniformly distributed random distribution, find the position such that V, so that zeta is in where you want it to be, and depending on where that position is, if it's 1, if the value is 1, it means that we have a new infection. And so what we're doing is we're changing I of t into I of t plus 1. Remember, I'm forgetting the S equation for now. And otherwise, if I'm in the second position, then I have the end of an infectious period and I of t decreases by 1. And then I increase the time and I continue. Okay. Now, there are issues with the Gillespie algorithm, and that's one of the reasons why you will probably want to use some packages later. So the main issue with Gillespie is that the inter-event time is exponentially distributed. That means that, remember that we have a step here, which is we get psi of t to be the sum of all the propensity functions. And we draw the time to the next event from this exponentially distributed, from a distribution that's exponentially distributed with parameter psi of t. So suppose that psi of t becomes very large. Well, you know that an exponential distribution with parameter psi of t has mean 1 over psi of t. That means that if psi of t is very large, then the mean time between events is going to become very, very small. Okay, so when psi of t becomes large, or is large at some point, then it is very likely that tau t will be very small. And as your population increases in your model, for example, then that can be very much a problem, because that means that as your as the weight of your events becomes large, the average time between events becomes very small, and the simulations just stop, essentially. Okay, so I'm going to illustrate this. This is a code that is on the on the repository, and I should point out it's also in the source code for these slides. Okay, these slides are, as I pointed out, in Sweave, and you can run the entire slide and it will generate these. You can run the code and it will generate these slides with different, not always. Point this out later, with results that might differ a little bit from the ones I'm showing you here in some cases. I'll come back to that. So what I'm going to illustrate is a birth and death process, essentially the simplest process that you can think of in terms of modeling the dynamics of a population. I'm going to have individuals that are born at a per capita rate b. So, okay, so if n of t is the number of individuals, then n prime of t is going to increase as bn of t, okay? And the death rate is per capita, and it's going to be at the rate d. So that means the differential equation for that system is n prime equals b minus d times n of t, okay? Let's do classic Gillespie. Let me show you how this works. So again, we set things as we had before. We compute the sum of the weights, which here are just B plus D times the population. We draw a time tau t from that exponential distribution. We make that vector, which the first one has Bn of t, the second one has 1. Essentially, we're dividing here. We draw a random number from 0, 1, and we find the position in this vector, which is such that the number at random that we have is between the two positions. And depending on whether we have 1 above or 2 a def, this is what we have. So let me show you the code. The code is very simple. As I said, it's on the GitHub repo and etc. So I'm going to make a function. This is going to be useful because I just want my code to run easily. That function has arguments, the birth rate, which by default I'm setting to 0.01. The death rate, which by default I'm setting to 0.01. An initial population, which I'm going to take to be 100, an initial time that I'm going to take to be 0, and a final time that I'm going to take to be 1,000. Let's think about days, or I'm not entirely sure what the units are, but let's say they are days. Okay. So this is a very convenient, I always point it out, this is a very convenient way of doing things in R. It's the fact that you can, normally I would have the parameters b, d, n0, t0, and tf, but because I set values, if I don't specify a value for those parameters when I call the function, then it's going to run automatically using these values, and you'll see that in a second. Okay, so what I want to do given these values is I'm going to make a vector to store the result. I'm going to make a very simple code, okay? A vector t will be the times, the vector n will be the states, so the population, and of course I initialize them with just one value, the initial time, and the initial population. Just to make my life easy, and here it's not really important, I'm also going to track the current value of n and t. Okay, so this is just n and t. I could look up the last value in the vector, but in this case, well, why not do it like this? Then this is Gillespie implemented in R. So what I'm going to do is, while the current time is less than or equal to the final time that I've set, I'm going to compute psi t, and psi t is, as I said, the sum of a propensity function, so b plus d times the current value of n. One remark, I'm going to use the exponential distribution, and it doesn't like, fortunately, doesn't like when you're using psi t equals 0. I'm using n current equals 0. I could check whether psi t is 0. I mean, it doesn't matter, it's the same. Okay, so just to make sure that I'm not asking for a random number from a distribution where I have a parameter 0, which causes an error, I'm just saying that if there's no individuals in the population, I should just quit. Okay, the function then returns without going any further. Then tau t is Rx is get me one random number from an exponentially distributed random variable with parameter psi t. Okay. Implement the moving forward of the time. So the current time is now the current time, the previous current time, plus this number that I've decided. I'm going to make the vector here, that vector v that I was talking about before. So this is the probability of birth. This is psi t, because there's only 2 events. Okay? If there were more events, I would have the cumulative weights taking place. But here it's just the first weight and the sum of the 2 weights, which is actually all that you have, divide by xit, take a uniformly randomly distributed number, take just one of them, and then find which interval zeta t is in this vector v. We have to shift by 1 because of the way find interval returns its values. And depending on this position that we found, we either have a birth or a death. Okay. Augment the vector of results. So add this new current state and this new current time and proceed. Okay, this is in the while loop. And when it exits the while loop, either because of a break or because TF has, the current time has become larger than TF, then it just returns as a data frame, so a column of T's and a column of N's. Okay? So this is what happens when the birth equals the death. So this is what we expect if you think about the ODE. If I have a model where n prime is equal to b minus d times n, and b equals d, so that means n prime is equal to 0. So what we expect the ODE to do in that case is to remain at the initial value, which I took to be 100. Okay, this is a stochastic process. It does not, of course, it always changes, but you can see that it's essentially moving around this value. One thing that I want to point out, no, I didn't show this yet. I should point out, if you run this code, the RNW code, the Swift code, you will get the same result exactly as here. Because I've set a seed, I'll come back to that in a second, okay? But I've set a seed to take a certain value. That means the sequence of random numbers always follows the same property. So if you're trying to use my code or to generate different solutions, bear this in mind. You'll have to change to another seed. I'll come back to that. Okay, so when the birth is smaller than the death, the ODE and the Markov chain predict the same thing, which is essentially the population is going to crash. Okay, because n prime is negative if you think about the ODE. That means the population is going down. So here you can see that it's going down. Now the problem with the Markov chain happens when you suppose that, in this case, birth is larger than death. Okay, because, so in that case, I know the ODE will go to infinity. Okay, the population there goes to infinity, and the same is true for the continuous time Markov chain. And you can see that here, I have stopped at about 300. And let me point out what's happening here. Let me show you. So the slide before that slide I just showed you, the population went to 0. And remember, we have encoded that if the population is equal to 0, the loop stops. So that's why it stopped. But on that last slide, I wanted 1,000 time units. But in practice, I got interrupted at 330 time units, essentially, because I lost patience. So that could mean just a control C in your code. But here, in fact, what I added, if you look at the code for the slides, you will see that I added a test on the size of a step size. And I think I said if the step size becomes that tau t, the increment in time, if that tau t becomes larger, smaller, sorry, I think it's 10 to the 1 e to the minus 8, so 10 to the minus 8, then stop. At that stopping time, I had a total population of 79,000 individuals, essentially, and the number of points, okay, the cardinality of the vector t and the vector v, which of course is the same, okay, because it's the solution, that was close to 160,000. Okay, so that means that to do 330 time units, it required essentially 160,000 time points, events. So these events are happening very, very quickly, okay? And so what was happening is that time moved very slowly. And here what I'm doing is I'm showing you how things work in terms of the time step. Okay, the time between events. So at the beginning, I have sometimes more than one time unit between two events. There's not a lot of things happening. When I take this random variable from the exponentially distributed this time to events distribution, I don't move much because the weight of the events is not very large. So things happen once a day, on average a bit lower than this, but there's still sort of large variations in the jump size. Now, as time progresses and the population n becomes large, so that the sum of the events becomes large as well, you can see that the time steps decrease. And on the red axis, I've showed you how many events are taking place in a given day. Okay, so I'm counting days here. Okay, so that means to move forward, for example, from 250 days to 251 days takes about between 500, close to 500, a bit more than 500 steps. And when you get close to where I stopped things, it takes over 3,000 jumps to move forward one day. That means essentially there's a jump every second in something which I was assuming was modeling something that was happening at the day time. Okay, so in practice, what do you do to simulate? When you run into this problem, there's an approximation method compared to the, the Gillespie I showed you before is what we call an exact method, because you can prove that that Gillespie algorithm gives you realizations that are exactly what you expect from a continuous time Markov chain that, that runs the model that you're planning to simulate. Okay. The tau leaping method, I'm not going to go into detail, but roughly the idea is that instead of considering single events, you can group things, and you essentially ensure that time moves forward by saying that you can consider not a single event to jump forward in time. Okay, so as I said, this is not the place for showing you this, but I'm going to show you how to use these packages, which I should point out also do exact solutions. So essentially you should probably start with an exact solution until you move to something that is adaptive, well, in tau leaping. Okay, so there's two main packages that I know in R. I mean, there's actually a third one. There's a Gillespie SSA without the 2, but SSA2 is an extension of Gillespie SSA, and adaptivetau. They both implement tau leaping, and they implement the stochastic simulation algorithm. So I'll show you how to use them. I'll point out one thing. So both packages do essentially the same thing. It used to be that Gillespie SSA2 was exporting events. I'll come back to that in a second. But actually now adaptivetau also does. Gillespie SSA2, and for that matter, adaptivetau does too. They can pre-compile stuff. It also has a slightly more compact syntax, but I find, personally, in my use of the code, that adaptivetau is more robust. I have run into issues when using Gillespie SSA2 on a parallel, in a parallel framework, with a large number of compute nodes. So I will explain that later. I'm going to illustrate using adaptivetau, but I will put some code with Gillespie SSA2, and you will see both of them are very similar. And I should point out, even the code for these slides includes some Gillespie SSA2 syntax as comments. Okay, so, and you will see they're very, very similar. Okay, so the initial setup using adaptivetau is simply, okay, declare that you're going to use the library, set your population to be 1,000. I'm here going to look at an SIRS, continuous time Markov chain. Okay, so susceptible, infectious, recovered, back into susceptible. So this is an endemic model. It's going to either go to an endemic equilibrium or to the zero equilibrium, depending on the value of the reproduction number. Again, this is not a course on epidemic models, but you probably know it, and in the worst case, look around, you can find, I mean, I've got slides on this, for instance, but there's plenty of things that can be found. So taking an initial population of 1,000, an initial number of infectious in the system to be 2. I'm just setting the initial conditions to be, I'm going to assume that R is 0, the number of recovered individuals. So here, R is for recovered, not removed, because they can loop back. So I'm going to assume that initially there are no recovered individuals. There's I0 infectious, and S, which is simply the total population minus I0 susceptible. The parameters that I'm going to use are gamma. I'm going to suppose that time units are a day, so gamma being 1/5 means that on average it takes you 5 days to recover from the disease. And nu, which is going to, I should add to these slides a little flow diagram. I will do that. So nu is the average time between movement from R back into the susceptible population. So 1/nu is the average time of immunity. So here I'm assuming an immunity of 50 days. And finally, I'm going to compute the transmission parameter beta by, so instead of picking some value, I'm going to assume that the reproduction number is 1.5, which is what you see here. And because that reproduction number is 1.5, this means that I can get beta. So in a model like this, beta, the reproduction number would be beta divided by gamma times the initial population in the susceptible compartment. Okay, so beta divided by gamma times S0. So I can compute beta knowing R0, 1.5, as gamma times R0 divided by S0. Okay, this is what I do. This way I know what to expect about the model. It's going to go to an endemic equilibrium. I mean, if I look at the corresponding ODE, it will go to an endemic equilibrium, and that's it. I'm going to take a final time of 100 days, and this is how to do it in adaptivetau. As I said, Gillespie SSA2 would be slightly different. In the very, very simple difference is that Gillespie SSA2 has those 3 components in the same function, essentially. Here I'm naming reaction names. Okay, so there's one that's called new infection, recovery, loss of immunity. These are the reactions. This is not required, but you will see it's useful later. So these are the reaction names. These are the reaction effects. And in Gillespie SSA2, they must be provided as a list. So that list says a new infection results in a decrease of 1 of S and an increase of 1 of I. A recovery is a decrease of 1 of I and an increase of 1 in R. And a loss of immunity is a decrease of R from 1 and an increase of S. And then I need a function which depends on the state parameters and potentially T. This is really convenient. I'm not sure Gillespie SSA2 has time dependence that easily incorporated, but adaptivetau does, which is really useful in some context if you have some parameters that depend on time. So what you need to do is return the rates at which each of these effects, each of these transitions takes place. Okay, so those rates I'm writing here are beta Si, gamma I, and nu R. Okay. Just in passing, this is not required. Here I'm making my life easy by using this syntax, which is very similar to syntax that is used usually in ODEs in R. I'm just saying I'm going to make my parameters. If you recall the parameters, I've defined the parameters to be a list. So if I want to access, for example, the value gamma, I would do params $sign gamma. By using this with x and parameters, it unpacks parameters, which means that instead of params $beta, I can just write beta. Instead of params $gamma, I can use gamma. And likewise, x is going to contain, because I've set my initial, you see my reactions are here, and my initial conditions are named. Okay, you see that I've said that first component is an S. That second component I call I, and my third component I call R. Because they are named, that means that when they come to the solver, it knows that X has components S, I, and R. So that means that by adding them to that command as well, instead of saying X of S, I can just say S. Okay? Here, for instance, I'm using a seed. I'm setting a seed, so set seed equals 1 means I'll always have the same sequence of random numbers. And then, so this is what I say here, okay? So I've set seed equals 1. If you want every simulation to be different, which in practice, unless you're preparing slides like here, that is what you want. Well, if you do want them to be different, for instance, you would say set seed of null. That would give you every simulation being different. Okay, so how do I do? Well, it's very simple. It's very much like what you do when you're using ODE 4.5 or ODE to solve your differential equation. You say SSA, so here I'm using the adaptivetau version. I'll come back to that in a second. SSA adaptivetau, you have to specify the initial values, which are the initial conditions that I set before, what the transitions are, and these are going to be the reaction effects list that I created. What is the rate function? And that rate function is that function reaction rates that I set. What are the parameters? Just params, as I did. And what is the final time? So they use TF as a single thing. I've defined it as T underscore F. Never mind. I mean, I could be more coherent, but never mind. So when you do that, the type of output that you get is, you see I've saved it in sol for solution. My solution looks something like so. It's got a column for time, which is the time at which the different events are taking place. It's got a column for S, I, and R, so states of the system. And so this is my initial condition. Remember, I put 2 infectious in I and 998 in S. Then at time 0.75 something, what happened is I got a new infection. At time 0.85, I got the end of an infection. Okay, I had 3 infected here. They became 2, with 1 individual becoming recovered. Then for about a day, 2 days, nothing happens. And then at that point, another individual finishes their infectious period and moves to there. Then what happens is I have a new infection. Then I don't know why it skips a line here. This is supposed to be another line, regular one, I mean. Then after 2 more days, essentially, there's a new infection happening, and this continues until 100. Okay? This comes out as a matrix. It can be useful to convert it to a data frame. If you do so, you'd say just that sol equals add as data frame of sol. Then that would allow you to use sol $time instead of sol element of the matrix column called time. Okay, so that's a little simpler, and it allows you to use a bunch of other R functions that are specific to data frames. And that's what the solution looks like. So remember, there's an endemic equilibrium. I've taken R0 to be 1.5. That's the prevalence, so I of t through time. You see it increase, and then I'm going to go to an endemic equilibrium. When I revise these slides, you can expect to see that I've plotted the endemic equilibrium of the ODE, which works very close to the endemic equilibrium here, and so I will revise and plot that just so that you see where you can expect the solution to go. Now, there's 2 very important options. I mean, one is not an option to using SSA adaptivetau. So the first one is, as I said at some point in a few minutes ago, was that you can also solve exactly. So if instead of saying SSA adaptivetau, you say SSA exact, then what you use is the traditional Gillespie algorithm. Okay, instead of a tau leaping algorithm, I would recommend to always start like this, and then if you hit a point where the solutions go, I mean, where your time doesn't move forward anymore, you will see very easily, then perhaps switch to an adaptivetau method. Okay. One very important option is report transitions. When you set it to true, what the solver is going to return is also the transitions that happened. Let me show you this. So again, I'm keeping the same seed, and I'm going to say, okay, instead of using the adaptivetau, let me use the exact. I don't change anything except that I'm adding this line here. Report transitions equals true. When I do so, instead of having just sol being this table, sol now has 2 components. It becomes a list. It's got fields dynamics, which is that table we already had, but it's also outputting another table, transitions, which are the transitions that occurred. Okay, and that's why I saved those reaction names, because one very useful thing to do is once you have that vector of transitions, you just name the columns by those reaction names. That will make your life much easier. Okay, so that's what I'm doing here. I'm saying that the transitions have names, those names that I gave, new infection, etc. You can give them whatever name you want, but this is really useful in the example later. Again, I will add a little flow diagram here. Let's just quickly say this is an SLIAR model. So it's a model that distinguishes between 2 types of infectious. They can be I, which is symptomatically infectious, or A, who are asymptomatically infectious. So essentially, it's a model for influenza. It was used as well for COVID, etc. All the diseases that have essentially a weaker form of the infection that is often undetected, but it's still infectious. So here I'm showing you the total prevalence, so the sum of I and A through time when I'm running this model. This is again, it's okay, this is the wrong, I should edit, it's an SLIARS. It goes goes back to S, this makes it an endemic model. Okay, so here I have an endemic equilibrium that I'm going to. But now, what thing that is really useful with Markov chains here, you can do it with an ODE, but it is really clunky, whereas this makes complete sense. What can we say if we look at transitions? So if I'm looking at transitions, I can write my code. So this code is in the slide, the code for the slides. You can see that here I've said, okay, my reaction is a new infection, and then at the end of my new infection, I have transition from L to I. Okay, so when I have an infection, a susceptible individual moves to the L compartment, and when they are done with their incubation period, they move from the L compartment to the I compartment. Okay, and in that case, the rate at which a new infection occurs is, so let me very briefly explain this. We typically assume beta SI would be the typical way to write this, but here I'm adding this plus eta A. So the idea is that asymptomatically infectious individuals, they probably don't infect people in quite the same way as symptomatically infectious ones. Okay, they have, I mean, typically we assume that this eta here is less than 1. This just says someone who's asymptomatically infectious is not quite as infectious as someone who is symptomatically infectious. Okay, so this would be the rate at which new infections happen. So this is the propensity function for this. And this is the rate at which individuals move from L to I. P here is, actually this should be P epsilon, sorry, not 1 minus P. I will adapt the slide. The P is the proportion of individuals who become symptomatically infectious. 1 minus P being those who become asymptomatically infectious. Okay, but that is not taking full advantage of what the Markov chains allow you to do. What if I do this? So instead of doing new infections, let me split the new infections, because I have two different events that can take place. I can infect someone when I'm an I person. So the effect is exactly the same. I have, whether I'm infected by an I or infected by an A, I end up in the same place. But the rates at which these things happen depend for infection by I on I, and for infection by A on A. Okay, so I've split this sum that I had in the previous slide into the part of a sum that corresponds to infection by an symptomatically infectious individual, and the part of a sum that corresponds to an infection by an asymptomatically infectious individual. That means that when I'm looking at my solutions, I'll be able to distinguish them. Okay, so let me just show you how you would plot this. I'm going to make this plot as an epi diagram. So I'm going to use something that's called incidence2, and a famous package if you do some R, ggplot2. To plot like this, I need a line list, what's called a line list from the transitions. That's a matrix which has columns. It has 3 columns at the minimum, which are time, value of whatever, and event. Okay, so instead of having several columns defining, for example, the time, the event, etc., what you want is each line in your matrix has one event, essentially, and indication of what type of event it is. I have functions there that you can look at that do that. And when you do this, then you get this type of plot. So this is the incidence. Okay, so this is not the prevalence. It's not showing me how many people are infected in the population. It's showing me how many people are infected at each time unit. I'm taking a day as time unit. By the way, I'm starting with the Unix epoch 0 number, which is 1st of January 1970. I could use another thing. I could just use values, but just for principle, I'm making them days starting at 0, hour 0, as Unix people. So this is showing you how many events are happening each day, but in particular, it's showing me in the deep dark blue, it's showing me the events that are infections from A individuals and those that are coming from I. And you can see this is really valuable because it allows you to distinguish between the source of your contamination here. But in a variety of models that you can think of, you'd be able to do the same type of thing. It allows you to pinpoint which source is contributing to an event. Okay, and the last thing I want to do, I don't want to make this thing too long, it's already long, but the one thing that I do want to talk about is parallelizing your code. We say that this type of simulations, when you're running a lot of simulations of the same continuous time Markov chain, is what typically is called an embarrassingly parallel problem, because each simulation is completely independent from the others. I mean, in general, unless you're doing things that are a bit weird, but in general, I can run each simulation completely ignoring the other simulations and just collect all the results and see what happens. Okay, so this is embarrassingly parallel because it's really simple to implement. You don't have to share memory and etc. You just think of each simulation as running independently from the others. So to do that, what we are going to do is we're going to run a function, to write a function. That's the simplest way. I mean, they can get much more complicated for more advanced computations, but the idea is that I'll write a function that is going to run one simulation, and then I'm going to use a fantastic little R command, which is parallel apply, to run this in parallel. And I'll just point out that, okay, if you want to compute anything like means, etc., on your solutions, and I will show you that in a second, then you will need to interpolate your results. Because remember, the one thing that's important with a continuous time Markov chain is that the time between events are randomly distributed. They follow an exponential distribution, but that exponential distribution depends on the state, which is itself a stochastic event. Okay, so two simulations of the same Markov chain are going to have a set of events that is happening at different times. If you want to compute a time average of your solution over over time, well, you'll need some way to compare those times. And the easiest way to do that is to actually interpolate to a very fine grid your solutions, and I'll show you that in a second. So the idea is the same as before. I'm making a parameter list, so there are more parameters than there were before. I need a total population. Here I'm starting with 2 infectious. I'm actually not sure that this is what I'm running in the code. I should check, but whatever. I think actually the slides I'm going to the results I'm going to show you have L0 equals 2, not I0. So I start with 2 latently infected, which should be an L, individuals. I'm looking at 100 time steps. My average time to recovery is 1/5. The average time of loss of immunity is 50 days. R0 is 1.5. Then I compute gamma. So here the R0 is a bit more complicated than it was in the previous model. I'm not going to explain, but just take it for granted that this is the value of beta that gives me an R0 equals to 1.5, depending on those other parameters. Okay. My initial conditions, I'm going to suppose that, oh yeah, I'm missing, yeah, definitely I need to adapt here because there's no L nor A, so I didn't finish copying my code. The slides will be adapted when they are posted. The transition lists, I can gain an infection Yeah, that's definitely an SIR model, not a not an SLIAR model, but it doesn't matter because the main idea is the same. So how do you run a parallel code? So you have to load the library parallel. And what I'm going to do is I'm going to again run this within a function. So I need to, and remember, so this is not yet the parallel version, but I will use this. So this is running one simulation. To run one simulation, I'm going to use the parameters. And as I did before, I'm going to assume that I have a list. I'm setting the seed to be null so that I have no problems of reproducibility. I'm calling the SSA exact, and you see that I'm doing all the options that we saw. I'm also reporting transitions, but I'm not going to use them in what I'm showing you. Let me show you how you would interpolate the results. This is very simple. So I'm just going to interpolate for I here. It doesn't matter. I mean, I could do all the variables, but let's just do I. So what I want is a certain number of t values from 0 to tf, which is 100 by default, from 0 to tf, and I'm going to take every 0.01 time units. And then I simply use this function, approx, which given an x, which is the times, and at which the events are happening, okay, and a y, which is the value of I at these times, the interpolates for this wanted t that I have here. And so I'll just rename things, and so I'm exporting the whole solution plus this interpolate I, which is simply the interpolated value of I. And now there comes the parallel part. So let's first ignore this if false. This is the parallel code. So I need to detect the number of cores. And I actually need to change this because this is not what I'm using anymore. Again, I'm setting this to 110 in practice. As I said, I'll post a slightly updated version of the slides. So this is simply, okay, the machine on which I'm recording this has 128 compute cores. R does not like this. So if this is a problem that you very rarely have, but if you are in the situation that I am, you have to be aware that you have to limit the number of cores, or you have to recompile R. This is easy to do, but you have to change. You either have to say that you want less than 128 cores, or you can recompile R, allowing for more cores. If you go to my blog somewhere, I think I explain how to recompile R for this. But anyway, so the idea here is I need to detect the cores. If you have a laptop, typically I would advise to do this. So detect cores is a function from parallel, and it says how many compute cores your machine can use. If you use all of them, your laptop will become, or your desktop will become completely unusable if you're doing heavy computations. So typically I set aside one core, just to say, okay, don't use everything, let me a little bit of room. Given the number of cores, you just call make cluster based on the number of cores. Okay. This here says to all the, so when you make the cluster, it sets apart, so let's say you have an 8-core machine, and you've done that detect cores -1 that I've done, then you've set apart 7 workers. Each of these workers needs to have all the information that they need to be able to perform the computations. So you have to think of them as running R from the command line, not from within RStudio or something like this, which remembers things. So you have to think about, oh yes, it's from the command line. What do my workers need to be able to perform that function here that I'm going to ask them to run. So to do that function, they need to know what adaptivetau is, because in here I'm going to use SSA exact. Okay. So here I'm evaluating the entire library. You could export just the function you want as well, using this second syntax, cluster export, but this is easy. Okay, so cluster eval is just evaluates on the cluster. Cluster exports sends to each worker something, and what they need to know is parameters, what the function run one sim is, and what the function reaction rates is, because when it's trying to run one simulation, it needs this function reaction rates. Reaction effects, remember, we've packed it in the, I didn't point that out, reaction effects and reaction names I have put in my parameters. This way I don't have to think about them. They're just there. They are passed to the function without having to think. Okay. So, but reaction rates stays as a separate function. Therefore, I need to provide it to the cluster. And then all I need to do is parallel apply on the cluster. Here, this is very simple because I am not providing parameters. I will have on the R for modelers something where I explain how to provide parameters to a parallel version of the code. It's a little bit more complicated, but here this is very simple. Okay, so I just need to say I'm going to run one simulation using the parameters. And because x doesn't matter here, I can just forget it. You see, it's a function of x, which doesn't use x, and it just says run one simulation. And then once this is done, I can just stop the cluster. So just as a remark, or actually this should be 100 here. As I said, there's a couple of edits of the slides I have to make. The code uses 100 and etc. But the slides, this is copied and pasted, so it appears a bit better than if it's Sweave spitting out the code. So this is the non-parallel version. And it's always good to have it, I'll point out, because debugging a parallel code is really complicated, because the errors happen in the workers, which are not sending back error. I mean, they send back error messages, but you can't dig into the error messages. So when you're initially parallelizing, it's a very good thing to run the non-parallel version. So you see, instead of parallel apply here, I'm using lapply, but the rest is the same. Of course, I don't name the cluster because this is not running in the cluster. So here I'm using lapply and doing this. The advantage being that I can actually debug this version. I cannot debug this version. And this is what 100 simulation of that SIS model look like. So what you don't really see here is that there's a certain number of solutions that crash, but you can see it in those two quantities. So here I'm using the, because I've interpolated the results, I have both, these are the actual solutions, but I then compute the mean, that's the red curve, of all these simulations, all these realizations at each instant of time. That red curve is the sum of all the values at a given point in time divided by the number of simulations. The blue curve, which looks much more like what the ODE would do, actually, and I didn't plot the ODE, I should add this. Perhaps when you get the revised slides, I will add the solutions to the ODE here. The blue curve is conditioned on non-extinction, because that's one of the characteristics of the Markov chains that's really good compared to ODEs. R0 is 1.5 here, so in the ODE, what you expect is all solutions will go to an endemic equilibrium. In the Markov chain, I start with very few latent. I have 2 latent in my initial condition. Because of that, there are simulations, realizations, where the number of infected in the L plus I plus A actually goes to 0. And once it's at 0, it's finished, because I'm not adding new cases by immigration into the population, this means that once the disease is done, it's done. And you can see the quite large difference between the mean conditioned on non-extinction, the blue curve, and the mean altogether, which is the red curve. Okay, and that's, as I said, one of the beauties of Markov chains, because that doesn't happen in ODEs. Okay, the benefits very quickly. So here I was running the code for 100 simulations. There's this thing which is very similar to MATLAB, for those of you who know MATLAB. MATLAB has tick-tock. It's a library in R, it's called tick-tock. You start the counter with tick, you stop the counter with tock, and it returns the time elapsed between tick and tock. So if I'm running the code, the time when I compiled this Sweave file, every time it's different. Okay, because remember I set a seed that's different. Well, a seed that's null, that means every simulation is different. So in this case, for 100 simulations with the parallel version, it took 0.35 seconds. Whereas if I use the non-parallel version, I get 1.05 seconds. Okay, so you can see that slightly bigger, faster. It's 2.88 times faster, as a matter of fact, to use the parallel version than to use the sequential version, the lapply instead of parallel apply. A couple of remarks, and that will be the end of this. First of all, when you're doing parallel computing, you have to think about overheads. Overheads are everything that are things like setting up the workers. You remember I said there's this cluster eval queue. I have to evaluate tau SSA, SSA tau leap on each worker. I have to initialize them, etc. And that overhead can actually be quite big. Okay, so there's, if you have a small number of simulations, it's probably not always a good idea. And that's particularly true if your code runs quickly. I mean, remember what I was showing you here, 1 second for 100 realizations of in the sequential version. Okay, I've gained 2.88 times by doing in parallel, but is that really worth it? But also, the setup time increases with the number of cores, because when you're setting up a cluster, for example, on this machine, if I'm setting up 110 cores, it takes more time than if I'm setting up 8 cores on a laptop. And just to give you, I cheated a little bit, the serial version, where everything is included, there's no overheads, took 1.015 second. But what I wasn't showing you is I was showing you the time for the parallel part. So I actually put my tick-tock here and there. But I also put another tick-tock between here and stopping the cluster. And if I look at this one, this is the overall time, you can see that this one is actually larger than the serial version. Now, one major difference is if your simulations take a little time, or if you're performing 100,000 simulations rather than 100, then the 2.88 increase factor here is going to make a lot of difference. And I'll point out, I mean, much of the code that I'm running, the factor that I get by running on a machine like this one with 128 cores is more of the order of 20 or 30. So if I'm gaining, if 1,000 simulations run 30 times faster, like 100,000 simulations run 30 times faster, it's often a difference between an entire day. So if you think about 24, for instance, an entire day to run the simulations, if I'm doing them in serial, and an hour if I'm parallelizing. So there are substantial gains, but just be aware that they're not everywhere. Another problem that arises is because of RAM usage. So each worker needs a copy of the data. If your data is quite big, it often happens that to run some simulations or to run some computations, you need a gigabyte, a variable that's a gigabyte or something like this. Well, if you need to make 100 copies of 100 gigabytes, of a gigabyte, that means that before you even start computing, you need 100 gigabytes of RAM in order to do that. So for example, that's one of the reasons I'm using this machine. I've got 192 gig on it, so I can run some code that I absolutely cannot run on other machines just because of the size in RAM. Also, when you're generating results, these can become quite big. Remember, so for example, if you look back to the birth and death process, where we had about a little under 200,000 data points, time points for the solution. Well, if I'm running 100,000 of those simulations and I want to keep all the results, and each simulation has 200,000 data points, things start to accumulate. So oftentimes you'll have to make decisions about what you want to keep. So for instance, if I go back to this code that I showed you earlier, what I was returning here is all the solution, which includes the transitions and the interpolated value. Well, it might at some point be more sensible to, for example, not report transitions if you don't need them, or for example, just return the interpolated values if that's all you need. Okay, so that's an important point, because when you're running a lot of simulations, it's very quick to get big in memory. One thing you have to remember also is there's nothing forbidding you from running the code for some time here, saving the results, running the code again between the call to making the cluster and stopping the cluster. Okay, so you can segment the work into subunits. Okay, and so this is something, well, when you start doing a lot of simulations like this, you will run into, and these are things to bear in mind. And that is all I wanted to say about this topic. Oh no, haha. Yes, just one last thing. Amdahl's law. So this is actually very well known. Oh, that's nice. This is a well-known property of algorithms that run in parallel, and there's a way to compute actually what speed up you get from executing a whole task in parallel based on what part is benefiting from being in parallel as compared to the proportion of the execution time that were already used. Okay, so and this is when you look at how parallel algorithms work, this is something that that shows up, and I'll just point out what that means is that there is a theoretical limit. So for instance, I've got 128 cores on here. If I get 128 cores working, I will not get 128 times amelioration in my result. There is a limit to how much I can gain. Okay, now we're done for good.